All right, good morning, everyone. The lecture today is going to focus on online planning and policy search. And we're going to start off talking about some of the differences in offline versus online planning, and then move into the actual online planning algorithms themselves and discuss some of the strengths and weaknesses of each one. And we'll also briefly look at some examples of hybrid planning approaches that have seen some large success recently, like AlphaZero style approaches, and how some of these hybrid planning methods can be extended to language model applications as well. And then we'll wrap it up at the end with policy search. And so the goal throughout all of this, right, like always, is to have this connection back to the bigger picture. So if you ever feel like you're losing that connection throughout any of this, just feel free, pop your hand up and ask a question. Okay, so starting off with offline versus online planning methods. So offline policies typically are pre-computed before any actions are taken in the actual real-world problem. And often these offline policies are solving over the entire state space. Okay, so they're trying to prescribe an action to take from any state that we're in. Online policies, on the other hand, are finding actions based on reasoning about the reachable state space. So they're planning forward from the initial state and looking at all of the different possible transitions that could occur from this initial planning state. And typically these online planning methods are using this receding horizon planning scheme to plan over that reachable state space. And so this idea of the reachable state space and receding horizon planning are sort of the foundation here of all of the online planning methods that we're going to be talking about. So we're going to dive into both of these concepts, lay the foundation for online planning, and then go into the algorithms themselves. So looking at the idea here of the reachable state space and receding horizon planning, starting with the reachable state space, I think this is a great graphic to sort of get the intuition here for what we're talking about and connecting it back to your life, right? So your reachable state space today is all of the states that lie in the future for you. So all of the different actions that you could take, whether you accept a certain job offer or move to a different city, those are all different actions that will affect the future trajectory of your life. So that's what's reachable from your current state today. What's no longer reachable to you is the actions that you took when you were 12 years old, right? So whatever you did when you were 12, no longer reachable from your current state. And I recognize we're at Stanford, right? And a lot of you are extreme high overachievers. So if you are 12 years old and you're taking this class, then that is still in your reachable state space, and I will correct that for you. But I think for most of us, it's no longer reachable. So connecting this same idea here to a game setup and using chess as this example, the reachable state space here would be looking at planning from this current board state of the chessboard that we show there, and looking at all of the different actions that we could take from that initial state and how they would transition us. Okay, so this would be looking at maybe I'm going to move my pawn to d5 from that initial board state. What state would that transition me into? And then what are the other states that I should move to from there? Okay, so offline policies, on the other hand, they're going to be looking at planning from every possible state, right? They want to prescribe an action to take from any state that you could be in. So the offline policies are going to be concerned with the beginning game strategy, so opening moves. They're going to be concerned with mid game and end game, all sort of in one, whereas the online policies are only going to be focused on planning from that current board state. So that's sort of highlighting the difference here between the two. And this is directly connected to this idea of receding horizon planning, because in receding horizon planning, we are essentially just planning over that reachable state space. Okay, so the way that this works is we're going to plan from the current state up to some depth or horizon D. We're going to take an action, and then we're going to just transition to that new state and replan. Okay, so this is very similar to what we've already seen. And so in this chess example, right, we've already shown the planning here up to a depth or horizon D. We're then going to take one of those initial actions. So let's say this is like moving our pawn to d5. We take that action, and then we transition into that new state. And then all that's going to happen is we just replan from that new state, and we repeat this process. And so that's where this receding horizon aspect is coming in, is that we are planning to that horizon. we then take an action and we just shift that horizon over. So you're never actually reaching that horizon that you're planning to. You're just continuously sort of shifting it as you take those actions and transition into the new states. And so a great real-world example of this receding horizon planning is in autonomous driving. And this is an example from Waymo here. And what you're seeing is the car's current plan is shown in green there. And so as more information becomes available to the car, it's going to update its plan as it sees that car veer into the intersection. And then so it's modifying the plan, replanning, executing that new updated plan, and continuing on. Okay, so this is a great example of how you're planning up to some horizon, you're taking in that new information, and then you're replanning as new information comes online. Yes?
Between offline and online methods, like, is there one that's better at taking into account like all future rewards versus?
Yeah. So the question was, between offline and online planning, is there one that's better in taking into account the like future rewards or future information that you'll receive? I'd say no, not necessarily. It would sort of depend on, one, the problem that you're working with, the size of the state space and action spaces that you're dealing with. And later we'll talk about the hybrid planning methods, which are really seeking to combine sort of the strengths and weaknesses of online and offline planning into one approach there. But yeah, that's a great question. So connecting this receding horizon planning back to what we've sort of seen in this agent acting in the environment, taking an action, receiving some observation, and then replanning from there. That's exactly what receding horizon planning is doing, okay? And it's just relating that to this idea of the reachable state space and planning purely over what's reachable from that current state. Okay, so that's sort of the big idea here with the foundation of the reachable state space and receding horizon planning. And so we're going to be building on this foundation as we go throughout the lecture today. And so now kind of zooming out here to the big picture, a common theme that we're going to see with these online planning methods is that typically the more time we spend searching or planning forward over different possible futures, the better our resulting policy is going to perform. And a way to kind of get some intuition here is if you're familiar with this idea of System 1 and System 2 level thinking, where System 1 thinking is this fast, sort of intuitive, quick reaction style thinking. And System 2 is more of this slow, deliberative thought process where you're thinking over possible actions, you're spending more time thinking before acting. Okay, and so we're going to see this sort of trade-off here between the System 1 and System 2 styles of thinking in online planning. And so a great example here, connecting this back to our chess example, is bullet chess. And so bullet chess would be this sort of analogy to the System 1 type of thinking here, where in this bullet chess scenario, it's a version of chess where each player has 1 minute on the clock to use for the entire game. So this requires the players to think and move pretty quickly where they would have to rely on this sort of intuition and pre-memorized board patterns as they move pieces around quickly. And so that would be this example of System 1 style of thinking applied to chess, where you're sort of just quickly moving from board state to board state without spending too much time thinking about what is my opponent going to do in response to this. The other side of this is System 2 thinking, where you would now be spending more time sort of evaluating many different possible futures that could occur. So this would be, for example, you're thinking about, okay, if I move my pawn to d5, what is my opponent going to play in response to that? And then how am I going to play in response to their response? And then how are they going to play in response to my response, right? And so rolling this out sort of several steps into the future, and then going back to the start and saying, now what if instead of moving my pawn first, I move my bishop? And how will that change their response? So you're doing many possible different evaluations here of this strategy into the future instead of just doing these quick sort of reactive moves. Okay, so that's this difference here between the System 1 and System 2 style of thinking. And so this is directly related to what we're going to be talking about now, which is this idea of policy rollouts. And so we're going to use this idea of policy rollouts here to be able to estimate the utility of a policy. That's sort of where we're going in this direction. But first, just what is a policy rollout here? So in order to perform a policy rollout, we need two things. The first thing that we need is a policy. Okay, so recall that we have this policy, pi of s, And this is prescribing an action for us to take in some state S. Okay, and so for our rollout policies, typically our rollout policies are going to be stochastic, meaning that this is a distribution. So given some state, we have a distribution over actions that we will take. Okay, so we can sample an action from this stochastic rollout policy. So that's the first thing that we need to perform a rollout. The second is a model. So we need a model of our transitions and a model of our rewards. So we're going to have some transition function here that tells us, given an action in a specific state, what states am I likely to transition to next? So this allows us to sample the successor state transitions from this transition model. And then we also have our reward model. Okay, so we have this RSA that gives us a reward for taking action A in state S. So this is sort of what we need here to perform these policy rollouts. Once we have these, we can go through our policy rollout example. So looking at this board state, right, that we're going to be starting from, we're going to use our rollout policy. And so our rollout policy here could just be a random action. So it could be just moving pieces around randomly, or maybe we have some sort of offline learn policy specifically tailored to chess that we're going to use to play. Regardless of what our rollout policy looks like, we're going to walk through this example. Okay, so we have our initial starting board state. We're then going to sample an action from our rollout policy. Okay, so our stochastic rollout policy is going to be this distribution over actions, and we're just sampling an action to take. Let's say that the action we get is move knight to e4. So we're going to move our knight to e4, and then we're going to sample a transition from our transition model. Okay, and so what we're doing here, just to sort of simplify things a bit, because we do have an opponent that we're playing against, right? So we're sort of baking their opponent strategy into the transition model. All right, so our opponent, for example, could be playing randomly, and we're modeling them as just a random agent. Or we could, again, have some other policy that we've sort of modeled for our opponent, and that's baked into the transition model. So when we sample a state from the transition model, we're assuming that's included the opponent's play inside of that, just to keep things simple in this example. Okay, so we sample a state transition from that, from our transition model, we receive a reward, and then we transition to that new state. So here, in response to us playing knight to e4, our opponent moved their pawn to d5. And now we're just going to repeat this from this new state. Okay, so we're just going to sample an action from our rollout policy. Now that action is bishop to d5. So we move our bishop to d5, and we sample an action from our transition model, and we receive a reward. Okay, so then we're going to transition to that new state. Now it looks like our opponent played queen to d3 and took our bishop, so we're probably going to receive a negative reward for that. Queen to d5, sorry. But yeah, we're still going to receive a negative reward there. And then this is just going to continue. So we're just going to sample a new action from this new state and continue on rolling this policy out into the future. And so this is going to continue until we reach some depth or horizon here, d. And that's going to be the extent of our policy rollout. And so the result of this policy rollout is a trajectory, right? We've received this trajectory represented by tau here of states and actions that we took along this policy rollout. And we also got rewards as we went, so we can keep track of the sum of discounted rewards here that we received along that rollout trajectory. And so this gives us sort of an estimate of how did our policy do along this specific rollout. And we can repeat this now, not just over one single policy rollout, but we can do this over multiple different policy rollouts. And this is the exact same sort of idea that we looked at before of evaluating multiple different possible futures using this policy rollout. And so for each one of these rollouts, we're going to get a reward for each of those rollout trajectories. And that's going to allow us now to estimate the utility of following this particular policy. Okay, so all we did was we just started from this initial state. We followed our rollout policy by just sampling actions and states from our transition model. We got rewards for doing that. And now we're going to use those rewards to estimate the utility of this particular policy. Okay, and that's going to bring us to our first online planning algorithm that we're going to talk about. But first, how can we actually do this estimation, right? So we saw that the reward that we got along a specific trajectory tau is just the sum from t equals 1 up to that rollout depth d. And then it's just the discounted reward. So we have some discount factor and the reward that we received. Okay, so now we want to be able to estimate the utility of our rollout policy that we're using. So the utility of the rollout policy we're going to write as u pi of r. And this r here is just to denote that this is following our rollout policy, okay? Because there's going to be a distinction here in a second. So that r is just saying this is our rollout policy that we're using. So the utility when following our rollout policy from a specific state, we're just going to approximate this as the average of the rewards that we received. Okay, so if we performed m policy rollouts, then we're just going to average up those rewards that we got along the m policy rollouts. So this is just going to be 1 over m, and then just all we're doing is taking the average here of those rollout trajectories. Okay, so we just performed m policy rollouts. We got m trajectories corresponding to that, and then we're just averaging those rewards there. And so we're just simply approximating the utility from this state following our particular rollout policy using those m policy rollouts. And so this is going to bring us now to the first online planning algorithm that we're going to be looking at, okay? And that is look ahead with rollouts. So the way the look ahead with rollouts algorithm works is kind of just in the name, right? We've seen the look ahead equation before, which is given by the following. So we're going to have the immediate reward that we receive plus the discount factor times the sum over all of the possible states that we could transition to, the probability that we're transitioning into those states, given that we took action A in state S, and then the utility of being in that new state. Okay, so this is just the look-ahead equation that we've seen previously. And we saw that we could extract a policy from this look-ahead equation simply by taking the argmax over actions, right? So that's how we can extract the policy from this look-ahead equation. So if we just now take the argmax here over actions, that's going to give us this policy that we can extract. Okay, so now notice the difference here. This is the online planning algorithm policy, the look ahead with rollouts policy that we're using. It's different from the rollout policy. And so what we're using this here for, so look ahead with rollouts, we're simply going to be estimating this utility. So instead of exactly computing this utility, we're now just going to estimate this utility from state S prime using M policy rollouts. Okay, so that's all we're doing. We're just saying that this is going to be replaced by using this rollout policy to estimate this utility from state S. Okay, so all look ahead with rollouts is doing is taking that look ahead equation, and we're just simply replacing this utility here and estimating it with M policy rollouts using some rollout policy. Okay, so that's all that's going on in look ahead with rollouts. Question?
And then the original look ahead equation was that was like unlimited number. I was like trying to see how far these things can see, or is this a main difference that like we only are looking at like a limited number of things versus that?
Yeah. So the question was, what's the main difference between this look ahead with rollouts and the original look ahead equation? So the original look ahead equation, we would be going over all actions, all possible states we can transition to, and then evaluating this U of S prime, right? So we sort of have this recursive step of then we would have to look at the utility of being in state S prime, which would then sort of evaluate to the immediate reward. And so you'd be going on into the future until you reach some base case depth that you're searching to. So that's one of the differences, which is now sort of just being wrapped into this policy rollout where the depth that we're going to in the rollout, remember, so we have this rollout depth here. So if we're going to, a depth of 10, that's going to be maybe a worse approximation than if we were going to a depth of 100 in our rollouts.
How can we substitute in the utility of the rollout pi when we may not go to all the possible states that it actually does transition to?
Yeah, that's a great question. So the question was, how can we use this sort of substitution here when our rollouts might not go to all of the possible states that you could transition to? That's a great question, and that's one of the limitations of using policy rollouts to estimate the utility, is that you might not necessarily visit all of the possible state transitions. So if you're only using a limited number of rollouts, then your variance estimate of the rewards that you receive are going to be high. So the variance will decrease with the number of rollout policies that you're performing. So that's sort of the trade-off, is that one of the limitations here is that you have to do this, right, over all actions, all next state transitions that you could go to, and then perform M policy rollouts in each of those. Okay, so if you have a large state and large action space, this is going to get a little computationally intensive there. Okay, and then the other limitation here is that it also requires having that rollout policy to begin with, right? So if your rollout policy to start with is a random rollout policy, then you're likely going to improve upon that random rollout policy, right? Because you're acting greedily with respect to that rollout policy. But just improving over a random rollout policy might not be that good, right, in the grand scheme of things, applying that to your actual problem. Because if you're just doing better than random, sure, you're improving, but you might not be performing that well in the actual problem. Okay, so those are some of the drawbacks here of the look ahead with rollouts method. Okay, so that's going to bring us to our next online planning algorithm, which is forward search. And so forward search is focused, instead of just approximating the utility by using a few rollouts from a rollout policy, forward search is looking at building the entire search tree of all states and action transitions up to some depth. And so that's the way that we're able to determine now the best action to take from an initial state by looking at all possible transitions that could occur. Okay, and so this visualization here that we're showing is for 3 states and 2 actions up to a depth of 2. And so when we talk about depth here in these tree search-based methods, what the depth means is we're starting at some initial state, right, shown by S, and then going to a depth of 1 would be this sort of first branching on the states. So that's depth 1, and then depth 2 would be at the bottom here, doing that next level of branching. And so we're going to be talking about the computational complexity here of these algorithms. And for forward search, we're going to be looking at first the branching factor. Okay, and so the branching factor for forward search is going to be the size of the state space times the size of the action space. Okay, and so what this branching factor here is telling us is how quickly is this tree going to grow as we go down in depth. Okay, so every time we add on another depth to this tree, we're going to grow that by a factor of the size of the state space times the size of the action space. The reason for that is because you can see sort of in this visualization that we are branching on all of the states and all of the actions. So that's the factor by which this tree is going to grow. Okay, so that's this idea of branching factor. And the computational complexity of the forward search algorithm is directly related to this idea of branching factor. So the computational complexity here using this big O notation is just the size of the state space, the size of the action space, up to raised to the power of D. So the depth of the search tree that we're going to. And if you haven't seen this big O notation here before for computational complexity, you can think about it, this is just a way that we can compare algorithms and sort of get a sense of how much work do we expect to have to do when we're performing this specific search algorithm. Okay, so a good way to look at this is in our example, right? We have 3 states, 2 actions. So 3 times 2 to a depth of 1 is 6, right? And you can see at sort of that first depth, we have 6 nodes in that layer of the search tree. Going to a depth of 2, we would have 3 times 2, 6, raised to the power of 2, which would be 36. And there are 36 states that we've now branched on in that second depth. And so this would continue, and you can see that this, even with only 3 states and 2 actions, this is going to blow up quite quickly, going to a depth of 10 or so. Okay, and so that is one of the limitations here of forward search, is that while it's nice to be able to construct, right, the entire search tree and get this perfect solution to it, we're sort of limited here by the branching factor, right? S times A is not great, especially when we're working with real world problems that have extremely large state spaces and action spaces. And then you're raising that to the power of the depth that you're going to. So it becomes not super practical in some large real world problems. And so that's where the branch and bound algorithm comes in, is it's attempting to reduce this exponential complexity in forward search by reasoning about bounds on the value function. And so branch and bound requires knowing a lower bound on the value function and an upper bound on the action value function. Okay? And so with these bounds on the with the upper and lower bounds here, what this allows us to do is it allows us to prune parts of the search tree. Okay, and so pruning is going to occur when the upper bound of an action at a state is lower than the lower bound of a previously explored action from that state. I think when you see it written like this, you're like, I have no idea what that is saying or why that would be the case, right? So I think it's helpful to sort of see an example and then come back to that statement, and it'll make a little bit more sense. But essentially what this is saying, so first, just looking at this, we have this upper bound on the action value function, okay? So this is saying this is the best possible that we could ever hope to achieve by taking action A in state S. Okay, so we could never do any better than this upper bound estimate here. And so what we're saying here is maybe we've explored a different part of the search tree already, and we've gotten some utility estimate that we're going to call U-best here. Okay, and so we used our lower bound estimate to come up with this best utility estimate on some side of the search tree that we've already explored. Now what we're saying is we're coming to some new part of the search tree we haven't yet seen, and we're looking at an action from that particular state. If this upper bound here, meaning the best possible I could ever hope to achieve by taking this action in this state, is less than that best utility that I've already seen so far on some other side of the search tree, then it makes no sense to take this action from that state, because we know for certain we could never do any better than what we've already seen over there. Okay, so if our upper bound estimate is less than the best that we've already seen, don't waste our time exploring that part of the search tree, because we know we're not going to do any better. Okay, that's the whole intuition here in branch and bound. And so how this works just with this visual example here, this is that same search tree that we looked at for forward search. So let's say that we've already explored this left side of the search tree, and we haven't done any pruning in this case. Okay, so we've explored that whole left side, and we get some best utility estimate using our lower bound on the value function. So we get our best utility estimate from that left side of the search tree, and now we're going to look at the right side of the search tree. So we're looking at this initial action to take from that initial state. And we're going to ask, is the upper bound estimate here, so the upper bound on our Q value function, meaning the best possible we could ever hope to achieve on this right side of the search tree, is that less than the best utility I saw on the left side? And if it is, then we're just going to prune off the rest of that search tree and not bother wasting our time exploring anything that lies on that left side. Question?
When you calculate U best versus like the Q value of like this like topic here, how far down are you going in the calculation?
Yeah, great question. So the question was, when you're calculating the U-best utility estimate versus the upper bound on the action value function, how far down in the search tree are you going? And so to get U-best, we are going all the way down to the depth of the search tree. So we're going to the very base level. And once you get here, you have that's where the lower bound comes in. So this is where you would say, okay, beyond this, I'm going to estimate the utility at this state using that lower bound estimate. Okay, and then that gets sent back up the tree. And that's why you end up with U-best being a lower bound, is because you use this lower bound estimate at the bottom of the search tree. The upper bound estimate, though, on the Q function is only looking at that state action pair. So that's where this would require you to have some sort of offline a priori knowledge of what that upper bound is going to be. Does that make sense? Was there another question? No? Okay. So, right, one of the sort of drawbacks here of branch and bound is that it requires knowing these upper and lower bounds. And where do you get these? Well, you have to come up with them yourself. And so in some game type environments, right, you probably have a reasonable estimate of an upper and lower bound on the value function. But in some real world problems where you're actually having to go and learn your reward function itself from data, you might not really have a good understanding of what are the bounds on this actual function that I'm working with. Okay, so that's one of the drawbacks here, is that if you don't have good bounds, the worst case computational complexity of branch and bound is going to be the exact same as forward search. The reason for that is because if your bounds aren't that tight, meaning you have like sort of loose bounds and they're really conservative estimates, you're not going to do any pruning of the search tree. And so if you don't do any pruning of the search tree, you just end up with back into forward search. Okay, and so if you're interested in seeing a sort of worked out example on a dice rolling game here, we posted that online that you can look at. It also walks through the code that's in the book and sort of relates those two to the example if you want to do that. And if you're watching online later, that will be up for you as well. All right, so that brings us now to our next algorithm, which is sparse sampling. And so sparse sampling is trying to get around this computational complexity that we have right now of s times a to the d. So that's really the goal here of sparse sampling, is reducing this branching factor of forward search and branch and bound. And the way that it does this is, instead of branching on all of the possible next states, it's only going to consider a limited number of samples of that state transition. Okay, and so when we're doing this, we're now just taking samples of that state transition, so we're not branching on all possible states. And as a result, we now have this approximation that's introduced. So sparse sampling is introducing this approximate sampling-based method into the search. And so what this looks like visually here is this is our original search tree from forward search. And what sparse sampling is going to do is that instead of branching on all of the states, it's just going to look at samples of that state transition. So we're still branching on all of the actions, but now we're only taking, in this example, 2 samples of the state transition. And those are shown in those dotted lines there. So we're sampling 2 state transitions instead of branching on all of the state transitions that could occur. And so as a result of this, we end up with a computational complexity here of, this would be, is everyone able to see this board? Yeah? Okay, cool. So we end up with this computational complexity now. Instead of the size of the state space, we're only taking m samples here of the state transition. So now we have a factor of m times a to the d, where presumably m is smaller than a. Otherwise, we wouldn't really be using sparse sampling here. Okay, so we've reduced our computational complexity now from this s times a to the d to m times a to the d using this sampling-based approach. The drawback here, right, of this algorithm is that you now rely on, well, how many samples are you going to take? If your state space, right, is 10 to the 20, and you're only taking 5 samples of that state transition, you're not going to get a very good understanding, right, of how you're transitioning based on the actions that you're taking. So now you have this trade-off of, do I take too many samples? Do I not take enough samples? How do I balance that trade-off? And so just summarizing the algorithms that we've seen so far, we've seen forward search, branch and bound, and sparse sampling. Forward search and branch and bound have a computational complexity of s times a to the d. And I think a good way to remember this is that s times a to the d spells SAD, right? And that is a SAD branching factor that you have, because it's just going to blow up as you go further down in the search tree. Sparse sampling then simplifies this, right, to m times a to the d, but now you're a little mad that you've had to use the sampling-based techniques to get this approximation there. Okay, so I think that's a good way to sort of remember the differences here in the algorithms, is that forward search, branch and bound make you sad, sparse sampling makes you mad. Okay, and now to just sort of gauge our understanding here, is if we use sparse sampling with m equal, so the number of samples here equal to the size of the state space, is that equivalent to forward search? Any ideas? Yes?
No, because you could just be stopping the same action over again.
That's exactly right. So looking at this, the answer is no, they're not equivalent. And you might be tempted to say, right, you might be tempted to say, well, if we're taking m here equal to the size of the state space, well, they have the same computational complexity, so they must be the same, right? But that's not the case, because what could happen is that in our branching that occurs, right, we have this onto the action, and then we're sampling these possible state transitions. You could end up sampling the same state from that particular action multiple times, right? It's not necessarily the case that you're going to get a unique state transition sample every time. In fact, if you have a really large state space, it's very unlikely that you're going to build up, almost impossible, right, that you're going to build up the search tree exactly uniquely with all of those state samples that you're taking. Okay, so it's possible that you could get super lucky and you sample a unique state transition every single time, but that's very unlikely in a large state space. Okay, so that brings us now to Monte Carlo tree search. And Monte Carlo tree search, I would say, is a pretty popular online planning algorithm for a few different reasons. One of the main ones being that it's practical and somewhat scalable to larger problems. And so the way that Monte Carlo tree search works is by running these M simulations from the current state. Okay, so that's how it's attempting to avoid this exponential complexity, is by running M simulations, sort of like these rollouts, but we'll talk about how they're different. And so just like in our policy rollouts, right, we require this model of the transition function and the reward function during the tree search. Okay, so we have to have this model in order to run MCTS. And during the simulations, we're going to be keeping track of two things here. So the first one that we're going to be keeping track of is the Q function. And so we're just going to, as we build up this search tree, we're just going to have this estimate of the Q function here. And then the other thing we're going to be tracking is just the counts. Okay, so this function here, NSA, is just counting the number of times we're taking action A in state S. Okay, so if we take action A in state S, we're just going to increment this count by 1. So we're purely just counting every time we take this action. And we can equivalently also keep track of the number of times we visited a state by just marginalizing out over the actions here. So if we just take the sum over the actions of NSA, we're just tracking now the number of times we've been in a state. Okay, so that's all we're tracking here in MCTS as we build up the tree, is this estimate of the Q function and the number of times we've taken action in a particular state. And then at the end, after we've built up the search tree here, one method that we can use is let's just choose the action that maximizes the Q function. There's other versions that you can use, like you could choose one that maximizes the action that you saw the most number of times. So whatever maximized the counts. You can do a combination of sort of a weighting between the Q function and the counts. There's different combinations. To keep it simple here, let's just say that we're going to do the max for the Q function. Okay, so how MCTS works sort of at the high level here before diving into an example is we have these 4 different steps. Okay, so the first step is selection. We have to select an action that we want to expand further. Okay, so this is sort of saying which action do we think is promising to look at more and sort of build up the search tree in that direction more. So we'll talk about how we actually choose actions here in a second, what we're actually using to select these actions. But for now, let's say that we selected this action in the tree. The next step involves expansion. So expansion is purely just sampling that state transition after taking that action. Okay, so we just select the action and then we sample a state transition, and that is the expansion step. The next step is the simulation step. So this could involve using a rollout policy. Okay, so if we used a random rollout policy, this would involve, just performing 10 random actions into the future and estimating the utility at that state there. You don't have to use a rollout policy though. There's other methods that you can use. For example, you could use an offline learned neural network that estimates the utility of being in a particular state. And then in the simulation step, you're just querying that neural network of saying, hey, what's the utility estimate in that state, and using that instead of the rollout policy. Okay, so I bring that up because we're going to talk about hybrid planning methods later, and I just want you to have that sort of sense of where does that fit into this MCTS setup. Okay, so you don't necessarily have to use a rollout policy here. For the example that we're going to be looking at, we will. And then after the simulation step, you're just taking that utility estimate and you're updating it back up the tree. Okay, and so then you're just repeating this process over and over of selection, expansion, simulation, and update. Okay, and that is MCTS at the high level. So there's a few things that we need to talk about here in a bit more detail. First is, how are we actually doing this action selection? So there's different exploration strategies that we can use. A pretty popular one and commonly used is the upper confidence bound. So the upper confidence bound metric is just the action value function plus this constant C. So this is a hyperparameter here, the exploration constant. And then it's times this log of the number of times we've been in a particular state over the number of times, just the counts here, that we took action A in state S. Okay, so what is this telling us? Well, it's sort of incentivizing, this right term is incentivizing us to take actions that we haven't yet seen. How is it doing that? Well, notice if the count function here is, so if we've never taken an action in a particular state, this is going to be 0, right? So this right side term is going to be infinity, and so this is going to force us to choose actions that we haven't tried yet. Okay, so this is like the exploration term. We're being incentivized to try actions that we haven't tried yet. This term here is more of the exploitation term. Okay, so this is telling us to take actions that we've seen from particular states that have showed us to perform well. Okay, so if we've seen it in the past to perform well, this is giving us that incentive to try it again. Okay, and so that's how the upper confidence bound is balancing this exploration with the exploitation term, and it's doing that through this constant c. So that's sort of weighting how much we're valuing the exploration bonus versus how much we're valuing the exploitation term. Okay, so that's the strategy here. Yes?
So to clarify, we start off with an action value function, and then we just keep updating that as we go.
Yeah.
Is our end goal here just to get a fully updated action value function so we know what policy we should perform?
What was the last part of the question?
Is the end goal to get an updated action value function so we know what policy we should perform?
I see, yeah. So the question was, is the end goal of doing all this to get an updated estimate of the action value function so that we know which policy to use? And yes, that is the ultimate goal, is that at the end, after building up this search tree, we want to take the action. In this case, we're using one that's greedy with respect to the action value function. But like we mentioned, you don't necessarily have to do that version of it. But yeah, the goal here is to build up this Q estimate here as to get it as good as possible to the actual real world problem. Okay, so that's the selection step. We're using this weighting between the exploration term and the exploitation term, right? And so this is a common trade-off that we have of should we try out actions that we haven't seen yet, or should we go with what we've already seen to be promising? And so how MCTS is balancing this, if you're using the upper confidence bound, is through this term here between that exploitation term and the exploration term. Okay, so I think it helps to see an actual example here to get a sense of how MCTS works. So we're going to be looking at 2048 to build up this example. And if you haven't played 2048, it's a pretty simple game, so we'll walk through it here. Initially, you're playing on this 4x4 board, and the game starts off with a 2 or a 4 randomly appearing somewhere on the board. And you then have 4 actions that you can take. So you can move left, right, up, or down. And if you played it on the phone, you're literally just swiping left, right, up, down. So if you move to the left here, what happens is all of the tiles are going to slide to the left, and then a new 2 or a 4 is going to appear somewhere else on the board. So if you move left again, the tiles will slide left, and then a 2 or a 4 again is randomly generated somewhere on the board. And so the goal of the game here is to get the tiles to add up to 2048. Okay, and so the way that you add tiles up is just by combining like tiles. So if you slide down now, the 2 and the 2 are going to combine and add up to 4. And so that's sort of how you get the tiles to add up. Now if we were to swipe left again, we would get the 4 and the 4 combine to make 8, and you just keep doing this until you add up to 2048. Okay, and so the general strategy here is that you want to keep your high-valued tiles in one of the corners, right? It doesn't matter which corner you're keeping those high-valued tiles in because you have a symmetric board, but that's roughly the general strategy. So looking at how MCTS would sort of build this up, starting from that initial board state. Okay, so we sort of open up the game. This is the first board state that we see. A 2 or a 4 is randomly generated on that board. In the first step here of MCTS, we're in this selection step, but we haven't seen any actions, right? So we're just going to initialize everything to 0. So all of the 4 actions available to us, we're just initializing those to 0. And that ends the first step, right? It was just purely initialization here. We can't really do anything after that. So now in the second step, we're going to come back to these actions that we've initialized, and we're going to look at our upper confidence bound metric. And we're going to say, okay, we want to select the one with the highest upper confidence bound. But in this case, they all have the same number of counts. They all have the same Q estimate. So we're just going to arbitrarily select the left action because it's the first one in our ordering, right? Because all of these, they would all have an exploration bonus here of infinity. So we're just arbitrarily going to choose left in this example. So we've done our selection step. Now we are going to go to the expansion step. And remember, the expansion step is just sampling a state transition from our transition function. So you notice we slid the tiles to the left, and then a new 2 or a 4 was randomly generated somewhere on the board. So that's our sample of the state transition. And then we've initialized all of the counts and Q estimates from that new successor state to 0. So now we go into the simulation step. And in this example, we're going to use a random rollout policy here. So we're just going to say, for this example, we're taking 10 random actions into the future. So this is literally just going to be randomly swiping left, right, up, down for 10 actions into the future. And that will bring us to a new board state. So we've kept track of the rewards that we received along this random rollout. And so from that, we get this utility estimate of 72 from this simulation step. And we're now going to update that back up the tree. Okay, so we're going to update our visitation counts now to 1, and then our Q estimate just becomes 72, since this is the only utility estimate we've seen from that state so far. And that would conclude this sort of first expansion of this left action. So now we're going to go back. We finished these 4 steps. We're going to go back up to the top of the search tree, and now we're back in the selection step. So in the second selection, which action should I select now? Well, now we actually have a value for the upper confidence bound here for the left action, and we're using an exploration constant there of 100. So this would evaluate to 72. But notice for the down, right, and up actions, those are all going to, again, be just infinite exploration bonus. And so again, we're just arbitrarily going to select the down action there, since we haven't seen it yet, and they all have that same infinite exploration bonus. So we select down. We're now going to expand on the down action. And so we sample a state transition. You can see we slid the tiles down. New 2 or a 4 appeared somewhere on the board. And so that concludes our expansion step. And now we just forward simulate. So we take 10 random actions from this new successor state. That brings us to this new board state. And we kept track of the rewards that we received along this rollout. And so that gives us this utility estimate of 44, which we're then going to update back up the tree. And so we update our visitation count by 1 and our Q estimate of 44. Okay? And now this would just repeat, right? We've done this for left and down. You can see that right and up are both going to have that infinite exploration bonus still. So in the next 2 steps, we're just first going to choose the right action, do the exact same thing we just did, and then we're going to choose the up action after that and do the exact same thing. Okay, so after doing right and up, following that same procedure, we're going to end up with the search tree looking something like this. Okay, and now it gets interesting again, because now which action are we going to choose? Any thoughts? Up? Yeah, that is correct. We're going to choose the up action. Why are we choosing the up action? Well, remember that we have the upper confidence bound here, and all of the counts for the specific actions are 1, right? They all have the same counts, so they all have the same exploration bonus. So we're not concerned with exploration in this case. It's purely looking at an exploitative step of which one has the highest Q estimate. So now we're saying, I want to sort of continue exploring, continue pulling the action that has the highest Q estimate, because that's what I saw to be best in the past. So we're going to choose the up action now. And we're going to now perform expansion on this up action. But in this case, when we sample a new state, right, it's very unlikely that we would see the exact same state that we already saw, because that 2 or a 4 is randomly being generated. So it's not likely that we're going to see that same exact state, and we end up with a new state transition here. So we're now going to perform that simulation step from this new state that we've seen. That's going to bring us to this board state, and we get this particular utility estimate of 44. That we're then going to update back up the tree. And so now we're just taking an average of the utility estimates that we've seen by taking this up action, right? So the first time we got 88, the second time we got 44, the average of those two is 66. So, and then we've also updated the visitation counts by 1, which gets us to 2. Question?
Can you just say again, like, what conceptually Q is?
Yes. So the question is, what is Q? Q is the action value function, which tells us the sort of utility, right, of taking an action in a particular state. So the Q function that we've seen, right, is just, if we write it out explicitly, it's just the immediate reward that we get plus the discount factor times the sum over all states that we could transition to. the transition probability, and then the utility of being in that next state. Okay, so we are passing in the action to take here, and so that's sort of forcing that forward with that particular action. Any other questions? Yes.
In the context of this game, 2048, how exactly is a reward formulated based on the board configuration?
Yeah, that's a great question. So the question was, for 2048, how is the reward being formulated here based on the board state? So there's a couple examples in the book showing different weighting functions that you can do on the tiles. So one example is that you can have sort of higher weights in the corners to incentivize your agent to sort of put all of the high value tiles in those corners. You can do an even weighting. So this example is just using an even weighting and just summing up the tiles on the board. But yeah, there's different sort of heuristics that you can use, or you can use just an end state of the game of 1 or 0. Did you win? That's a little bit more challenging because then you have to search for a really long depth horizon to get that any signal there. But yeah, there's different utility functions you can use there. Okay, great. So after doing this update, we're left with this search tree. And this process would just literally repeat over and over until you've either run out of number of simulations to perform, right? So in MCTS, you set the number of simulations that you're performing. You can also specify a time limit. So if you only want the algorithm to run for 1 minute, you can do that. And whatever the Q estimates are after that 1 minute are returned, and then you can make your action based on that. So it's an anytime algorithm, meaning you can stop it whenever, and the estimates that are returned are what you end up with. Yes?
Two quick questions. So I guess for the up action, the reason why we have 2 is because we just randomly generate another one. Is that one?
Yeah, so the question is, for the up action, why are the counts 2?
Not the counts. I guess why do we have 2 boards for this one rather than
Oh, okay.
on the same one?
Yeah, so the question is, why do we have 2 new board states? And that was because we selected the up action to expand on, and in that expansion, we sample a new state transition. And so in 2048, it's very unlikely that we would end up with the exact same state that we saw the first time, because every time we do that state sample, a 2 or a 4 can randomly appear in any of those open squares. So it's very unlikely that we would get a 2 showing up in that exact bottom left square that we saw the first time. So that's why we end up with this new state that's different from the first one that we saw.
And then also, I guess with Monte Carlo tree search, is it usual, or would you always expect to have gone through every single action at least once, just because of the upper bound or throughout the
Yeah. Yeah, so the question was, with MCTS, would you expect to always go through every single action? At least once. And if you are using the upper confidence bound, then the answer is yes, with a caveat, because if you don't have, say you have a really large action space and you only have a limited number of iterations, you might not be able to branch on all of those actions in those iterations that you're performing. But if you have enough iterations and you're using upper confidence bound, then the answer would be yes, because you'll have this infinite exploration bonus. And so you're always going to choose an action that you haven't yet seen relative to, unless you have an infinite Q value maybe, but then it's well, what's your Q value, which isn't really reasonable. So yes, with a star. Yeah.
Can you explain how the name upper confidence bound actually relates to the expression that you showed us?
Yes. So the question is, where does the name upper confidence bound come from? And you'll see that, I think it's in chapter 15 when we talk about multi-arm bandit problems. And so upper confidence bound is an exploration strategy that was originally developed for those multi-arm bandits. So how are you sort of choosing which lever of the multi-arm bandit to pull? And I don't want to get too ahead of ourselves skipping to that chapter, but essentially it's coming from that multi-arm bandit problem. Yes?
Is one of the drawbacks that you have to keep track of each possible state, and as you continue to go deeper into your number of steps, that takes up a huge amount of memory?
Yeah, so the question is one of the drawbacks of this algorithm that you have to keep track of each sort of possible state that you could transition to. And I would say that is a drawback relative to the other algorithms that we've seen, though, like forward search or branch and bound, where you're doing that branching on all of the state transitions. This sort of remedies that, and you only have to store those state transitions once you see them. So you're not storing every possible state that you could transition to. You're just keeping track of it as you go. But what we'll see sort of next, let me just show you this really quick. So if you ran this MCTS algorithm here on 2048 for 100 simulations, this is the resulting search tree that you would end up with. And here the blue is showing sort of higher Q values, red is showing lower Q values. And you can see that after 100 simulations, we have a pretty shallow search tree. And this sort of goes back to your question of the reason that that's occurring is because we have all of these successor states that we could transition to. In 2048, right, it's very unlikely that we would see that same successor state again. So we have this branching that's occurring on the actions, and we're ending up with the tree growing wider before it gets any deeper. And so that's one of the limitations. When you have this large branching factor still, your tree, even after taking all of these samples, like the furthest we've gotten here is just a depth of 3. Yeah.
Decrease C to overcome that, I guess.
Sorry.
We could decrease C to overcome that. Like it would grow more deeper than.
Yeah, that's a great point. So the point was that you could change the value of C here to overcome this shallowness in the search, and that's exactly right. So if you want to value the exploration terms less, then you could do that. You're still going to have the infinite count issue on that first step, but there's ways around that as well if you want to enforce going deeper in the tree. Okay, and then just really quickly wrapping up this example. If we were to continue on, we're not. I think we get the idea here of MCTS. But if we were going to continue now, which action would we select after this? Left? Yes, that is correct. We would select left. The reason for that is because if we look at left, down, and right, they all have the same exploration bonus, right? Because they have the same number of counts. And so we're looking at that pure exploitation, so we'd select 72. But now looking at left versus up, we would see that left has the higher exploration bonus because it's been visited less, and then it also has the higher Q estimate. So it's winning out on both of those, and we'd go with left. All right. So now just to make sure we're all on the same page here, how this would work, right, if we're playing sort of with an autonomous agent using this MCTS approach in 2048. The real board state that would be in the real world, right, is shown on the right. And the agent sees this board state, and it then goes and does all of this offline, not offline computation, but it's doing the computation sort of in its head, right, of building up this search tree. And so all of these forward simulation and rollouts that are occurring are not happening in the actual game, right? It's based on the agent's model of the game. And so the whole search tree is generated inside of the agent internally. And then at the end, the agent is going to say, okay, take the left action. We take the left action, and that's what changes the actual real world board state. And then the process repeats again after that. Okay, so just sort of clarifying the difference there between where the state transitions and everything is occurring is all being simulated by the agent, and then it's acting in that real world environment after that. And so, yes, question?
So when you said the process repeats after that, you still maintain the same tree, but you continue from the actual state you're in.
Yeah, so the question was, when the process repeats after that, so when you transition to a new state, do you keep the same search tree? And the answer is, if you're just doing a vanilla-based implementation of MCTS, you might not necessarily have that caching occurring of the counts and the Q estimates. But if you're doing a efficient implementation, you should be storing that as you continue on. So there's a few different variants here to mention. Just the tree search depth and the rollout depth. Those are two different things. Okay, so in the rollout depth in that example, we were doing a rollout depth of 10, just taking 10 random actions. You could also instead do rollouts until you reach an end game state. So until there's an outcome of a winner or a loser in the game. So that's one variant of the tree search versus rollout depth. There's also that value function estimate, so that I mentioned earlier. You don't necessarily have to use the rollouts again, right? You can use that offline learned estimate, and that would be this hybrid planning style that we're going to be talking about next. the exploration strategy that you're using, right? You don't have to use upper confidence bound. And the source of the model here is a big one, right? MCTS really only makes sense when you have a good understanding of the transition and reward model. Because if you don't have a good understanding of those models, then you're going to be wasting all of this time building up this search tree with all of these state transitions that aren't actually realistic for the problem that you're interested, right? So when you're sort of evaluating, should I use MCTS or not, it sort of comes back to, well, do I have a good understanding of that transition and reward model? If the answer is no, then you probably shouldn't be using this model-based tree search here, okay? So that's a big problem when you're looking at applying this to real-world problems. Yes?
On that topic, like with that transition model, like when we're out in the simulation step of the 2048 game, it sounded like we were doing like a depth of 10 where we were just simulating 10 steps in the future with totally stochastic actions like after we've chosen the initial action. So is our transition model then just like 0.25, 0.25, 0.25, 0.25 for like up, down, left, right, like after we've chosen that first action?
Yeah, okay, so the question was about the transition model we were using in the rollouts. In the rollouts, I guess we have a difference between the rollout policy, which that would be 0.25, 0.25, 0.25 probability for each action that you could take. But then the state transitions that occur as a result of those random rollouts, random action selection, is going to be based on our sort of game simulator that we have internally to us. So how we sample that state transition is going to be based on that.
Would that be like where the random 2 or 4 pops up on the board would be T, and then which direction that we go in would be I?
Exactly. Yep. So just to clarify, if you couldn't hear that, it was sort of where you're going is, or where the 2 or the 4 is being generated is, that's your transition model, and then the action that you're selecting is your rollout policy. Yes.
So we're not running this exploration step on the future rollout steps.
That's correct. Yeah, you're not using the upper confidence bound in the rollouts. Yeah. Yes.
And then can I clarify the tree search depth that we saw in the example was like that 3 that we reached?
Yep.
And then the rollout depth would be that 10 that we made it this evening.
That's correct. Yeah. So the question was about the tree search depth and rollout depth. So in the example, it was rollout depth of 10, and then the tree search depth that we showed after running 100 simulations was that we got to was 3 at that point. Okay, and then one other one just to mention at the bottom there is progressive widening. And so we saw that issue with the the shallow search tree occurring. So one method, right, was to reduce the exploration constant. Another way is that you can use this progressive widening, which is limiting the number of branches that can occur on your states or your actions, so that you sort of artificially force the tree to go deeper before it gets any wider. So that's another method that you can use there. So this is just sort of to show you that there's quite a few different variations that you can implement with MCTS, and that's another reason that it's sort of a versatile algorithm to use. All right, and so now connecting this to some of the hybrid planning methods, I think most of you have probably at least heard of AlphaGo from DeepMind, and there's several different versions of AlphaGo that have been released. There was the original, and then AlphaGo Zero, which is what we're going to briefly talk about today, and then Alpha Zero came later, which was a generalization of the algorithm to other games as well. And so AlphaGo Zero achieved superhuman performance in the game of Go. And the way that it did this was through this hybrid planning approach of an offline learned neural network in combination with MCTS and self-play. So the way the self-play step worked was essentially having the agent play against itself. Okay, so starting with this initial board state shown by S1, the agent performs Monte Carlo tree search using the offline learned neural network in the tree search. It produces this policy from the tree search and then samples an action to play based on that tree search that it performed. In the next state now, it's the opponent's turn, and the opponent is going to play the exact same way that the first agent did. So using the same offline learned neural network, same MCTS setup, it builds up the search tree and then plays an action sampled from that policy. And this process of the self-play just continues until the end game is reached. And at that point, we have this indication of who won the game. So that Z variable is telling us which of the agents won. So now we have this self-play demonstration, and we can use this then to update the offline learned neural network. Okay, so how that network setup was basically it takes as input the raw board state, so that S1, and then it outputs two things. So the first output is this vector of action probabilities, okay, so that's the P1, and that's telling you sort of the probability of selecting each action. And then the second output is the value estimate, and the value estimate there is just mapping to the probability that the current agent ends up winning the game, okay, so that's sort of this idea of what is the value of being in a particular state in this case. And so you can now do this, right, for each state that you saw during the self-play iterations and update the network parameters based on those examples that you saw during the self-play step. And so the outcome there, Z of who won the game, is then passed back through to all of these different training examples, and you're trying to match the action probabilities to what was produced by the tree search setup. And so you just repeat this process of self-play and then network parameter updates. And just by doing that repetitive fashion of this self-play and network update, AlphaGo 0 was able to achieve superhuman performance. So just looking at some of the results here, you can see relative to previous versions of AlphaGo and then AlphaGo 0. And here the y-axis is showing the ELO rating, which is a way of measuring human performance in these games. And the cool thing here is that if you look at just the raw network, so just the raw offline learned neural network shown on the far left, and if you played just with respect to that network, so just the action probabilities that were output and the value estimates, and playing with respect to those, you're actually doing quite a bit worse than the AlphaGo 0 algorithm. And so kind of mapping this back to what we talked about at the start with that system 1, system 2 level analogy, right? And extending this analogy, that's kind of like a system 1 style approach where you're just sort of quickly, greedily taking this intuitive board state into account and then playing with respect to that intuition. Whereas when you add on this system 2 level style of thinking of looking at multiple possible different actions using this intuition to guide you, you're able to get quite a bit of performance boost. And so still currently, no one yet has trained a raw neural network that is superhuman in Go. And it's definitely possible that this happens soon, but as of right now, no one has done it yet. DeepMind released a paper earlier this year that achieved grandmaster performance in chess without using search, but hasn't been done yet for Go. Certainly not saying it's not possible. It probably will be done eventually, but just not yet. Yes, question?
The playing by itself isn't just making samples. It's like, I guess when you're actually playing the game using AlphaGo 0, are you using search, or are you playing specific actions using search? This is like the actual neural network, or is it the other way?
Yeah, good question. So the question was, in the self-play step, how is the search coming into the algorithm basically? And so in the self-play step here. Let me go back right here. So yeah, essentially for each of those board states, the current agent playing is building up that MCTS search tree using the network estimates as it goes, and then it's sampling an action from that policy that's built up as a result of this search tree, and then it goes to the next action, the next agent to play. Yes.
So when you do self-play, do both players share the same MCTS tree, or do they have two separate trees?
Good question. I believe they both have different search trees. So I don't think that the search trees are being shared, but I would need to double check on that. Okay. So I think a really interesting area is extending these hybrid planning approaches to language model applications. And the same idea here of system 1 and system 2 kind of applies. And we're just going to briefly touch on this. This would be like a whole nother lecture or class in itself. But I think it's cool to relate it to sort of what we're seeing here with the online planning algorithms and how it's connecting to some of the current research. And when I say that this is a field that's advancing very rapidly, I think that's like a huge understatement because there's so many people working on this right now. But just like briefly looking at this, right? If the current language model setup with these autoregressive next token prediction is basically like looking at, okay, I chunk up the input into tokens, and then I'm purely trying to predict just the next token based on that sequence that I've seen. And so as a result of this, this is sort of like that system 1 level approach where we're just sort of connecting it to the AlphaZero style example, it's like kind of playing with the raw network, right? You're just taking the next action with respect to that raw network. In this case, the raw network being the language model itself. And you're kind of playing greedily with respect to that. So the system 2 level thinking here, and what people are pretty excited about is, what if you now take this hybrid planning approach of, instead of just that purely next token prediction, you're searching over this future sequences of tokens that could occur here. And as a result, you can sort of build up this better strategy using the hybrid planning approach. So I think that's a pretty interesting area. Certainly not the only area to make improvements here, but it's a direct connection to what we were just looking at here in the hybrid planning approaches. And then the last thing just to touch on here in these hybrid planning methods, this is a paper from Andy Jones that was looking at using an AlphaZero style approach on the board game called Hex. And so the main takeaway here, right, is that you have the train time compute on the x-axis, test time compute on the y-axis, and the lines here are showing the minimum train test time compute required to achieve a certain ELO rating in the game. And so this is showing, we can sort of think about this in our setup that we're looking at, right? It's kind of like offline on the x-axis, online on the y-axis, and how are you spending your compute between those two? So what this is telling you is that there's roughly a 10x. So if you reduce your train time compute by 10x, you would need to increase your test time or online compute by 15. Okay, so there's that 10 to 15 trade-off here. But what that's saying is that if you're investing a lot of money, right, in your offline learned neural network, you could save that money and instead invest it in some online compute and achieve the same performance, scaling down by a factor of 10 and scaling up by a factor of 15. Okay, so that's just one thing to sort of note, is that in these hybrid planning methods, you have this trade-off of where are you devoting your compute, and oftentimes you can gain some performance or cost savings based on how you're allocating it there. Okay, so I think that's just an interesting example, again, relating to what we were looking at here. All right, so that brings us now to policy search. And policy search is now focused on searching the space of policies without directly computing a value function. And so the reason for this is that the policy space, typically, depending on how we've parameterized our policy, is going to be lower dimensional and can be searched more efficiently than searching over purely the state space. Okay, and so how this is going to work is that we are going to introduce our parameterized policy. And so we're going to have this vector of parameters here, theta. So we're just going to have theta 1 to theta n. So we have n parameters here. These could be the weights and biases of a neural network. They could just be the parameters of a linear function or any type of function, right? So we just have these parameters here. And now we're representing our policy, pi, and we're going to write it as pi theta just to denote that it's parameterized by these, this vector of parameters. So we're still taking in a state, and we're still outputting an action to take from that particular state. It's just now we're representing this policy function or distribution by these parameters theta. Okay? So what's going to happen now is that we want to basically figure out how should we update these parameters in such a way that we improve our policy. That's sort of where we're going with this. And just like what we saw before, was that we could use these rollouts to estimate the utility of a particular policy. So now when we talk about the utility of our policy, right, we're going to say the utility here of following policy pi theta, and we can equivalently write this as just u of theta, and you'll often see it just dropped like that, because really what you're talking about is the utility of the parameters of that policy. So we're concerned about improving those parameters. And we can equivalently do the same idea here of the policy rollouts and approximate this utility just using m policy rollouts and getting those rollout trajectories here. Okay, so with a current policy parameterization, so we have some current policy parameter vector here, we're then going to perform m policy rollouts using that policy and then get this estimate of the utility of those specific policy parameters. So same idea, just now using a different policy setup here. Okay, so the first method here for policy search that we're going to be talking about is local search. And the way that local search works is we start, in this example, we have a policy with two parameters, theta1 and theta2. And the current policy parameters are shown in the center there, so that center white dot. The background is showing the true utility function. So we don't actually know this, right? This is unknown to us, but it's shown in the background for reference. And so local search works by taking a plus and minus step in each parameter direction. Okay, so for theta1, we're going to take a plus alpha step is the step size here, and a minus alpha step. For theta2, we take a plus alpha step, a minus alpha step. And then for each one of those candidate points, so we have n parameters here, so we're evaluating 2 times n candidate points. For each of those candidate points, we're going to perform m policy rollouts to get a utility estimate at that point. So in this case, we see from doing those policy rollouts that the best performing point is on the left, because the blue is higher utility in this example. So we're going to step now to that left best performing point, and then just repeat the process. So evaluate each of these candidate points using m policy rollouts, and then step to the best performing one, which is at the bottom. So we're going to step to that bottom point, and then just again repeat the process. So here again, the best performing point is at the bottom, so we step down there, and then that will repeat one more time. And now what happens in this case is that we evaluate the candidate points, but none of them are any better than our current policy. So what do we do in this case? Well, we're just going to shrink that alpha factor now. So we just shrink down, and in the next iteration, we've just stepped a little bit less. And we check to see if any of those outperform. None of them do, so we just shrink alpha again. And we'll just keep shrinking alpha until we reach some convergence criteria, and that will be the termination of the local search algorithm. Okay, so we're just purely making these plus and minus local changes to the current policy and seeing how that results in changes to the policy vector. Okay, and so some of the drawbacks here is that we have to use m rollouts for each of these candidate points, right? So we have 2n candidate points and performing m rollouts for each one of those. So if you have a really large parameterization, right, you have like 1 billion parameters in your policy, then that's going to be quite intensive to do. And it also requires setting that initial alpha step size that you're using. Okay, so that now becomes your parameter to play with. And so that's what brings us to the cross-entropy method. And the cross-entropy method seeks to improve on the weaknesses of local search by using a search distribution that we are representing by this p theta of psi here. Okay, and so again, this is still just our policy vector of parameters. But now we have this other set of parameters here which parameterize our search distribution. Okay, so if we're using a Gaussian distribution, this is just the mean and covariance of the Gaussian distribution. All right, and what we're saying then is that our policy parameters are distributed according to this Gaussian distribution. You can use other distributions in here as well. In this example, we're going to be using a Gaussian distribution. So how this is going to work is we're showing now the same theta1, theta2 setup, and the contours of the Gaussian are shown in white there. Okay, so we're just using a Gaussian distribution, and then we're going to take k samples of theta from this search distribution. And those are those white points that you see. So we've sampled k points from this search distribution, and then we're going to evaluate each one of those samples. We could use policy rollouts. You don't have to use policy rollouts to get this utility estimate. There's other ways that you could do it. In this example, we're using policy rollouts. So we evaluate each one of those using policy rollouts, and then we're going to refit the search distribution to the ones that are performing the best. Okay, and then we just repeat this. So in this case, the best performing samples are shown in red here. So those are the ones that perform the best, and we're then just going to refit the search distribution to those best performing samples. Okay, so we refit. This is what the new search distribution looks like. And then we're going to repeat the process, right? So now we're going to, again, take k samples from that search distribution. We're going to evaluate them all and then refit the distribution. Now you can see the new best performing are shown in red. So we refit and then repeat the process. And we just keep doing this until some convergence criteria is met again. And so you notice here we find a different local optima. So we converge to a different local optima. But also, sort of, what's the point of doing this, right? How is this different from local search? Well, remember in local search, we're evaluating 2n of these candidate points, and each candidate point is only changing one of the n parameters at a time. So the cross-entropy method is a little bit more efficient in how it's distributing these out, right? And we also have control over the number of samples that we're taking, right? So we are setting the K factor here. The drawback, though, is that we now have to choose this number of best performing samples. Okay, so how many samples do we keep around now becomes the trade-off, because on one side of the spectrum, if you choose to keep around too many best performing samples, your search distribution is not going to change much iteration to iteration. But if you take too few samples to keep around and refit to, then you're going to collapse that search distribution very quickly. So you have this trade-off of keeping around too many and not keeping around enough samples, and that now becomes your tuning parameter here. Okay, so just wrapping up what we've seen with policy search, we saw that we could still use the same idea of policy rollouts to get an estimate of how our parameterized policy is doing. And then we also saw that local searches just focus on these local changes to the policy, and then the cross-entropy method introduces this search distribution to improve upon that. And so wrapping up now with online planning and policy search, we focused today, right, on methods for online planning that were reasoning about states reachable from the current state that we're in and using this receding horizon planning scheme. And there was a variety of different approaches looking at pruning the state space, sampling state transitions, or replanning along trajectories that we've seen to be more promising. And then we wrapped up there with policy search. So I hope you found that interesting and helpful, and I'm happy to take any questions offline now. So thank you.